Alrighty, so energy. It's somewhere, I marked it. I'll get it for you. Somewhere. Quinn, what is energy?
A lot. That's my answer.
Well, there is a lot of energy in this room in the afternoon, it seems. Yes, that's true. But if you have to define energy, it's kind of hard to do. Everyone sort of knows when they see it. You see a little kid racing around, you know that kid has a lot of energy. But what is energy? A bit of a challenge. I'm not sure if it's all over the place. Okay, energy is the most central concept that underlies all of science. Surprisingly, the idea of energy was unknown to Isaac Newton, and its existence was still being debated in the 1850s. So it's a relatively new concept. The concept of energy is relatively new, and today we find it ingrained not only in all branches of science, but in nearly every aspect of human society. We're all quite familiar with it. Energy comes to us from the sun in the form of sunlight. It's in the food we eat. It sustains life. Energy may be the most familiar concept in science, but it is one of the most difficult to define. Persons, places, things have energy. We observe energy only when something is happening. Right now, you all have potential energy stored in you, but you can only really see it when something is happening, when you move, when energy is being transformed from one format to another. We're going to begin our study of energy by observing a related concept, that being work. So, and this handout actually, if you were to miss the entire unit, this handout would pretty much skim everything we're going to talk about, with the exception of springs, really. Okay, so it's sort of a very general introduction to the whole thing. The last chapter showed that changes in an object's motion are both related to force and to how long it acts. How long meant time. That is formerly when I've done momentum before. Ladies, now is the focus time. Please. So frustrating when I go through things and then you ask me the question that I've just explained because you won't listen. So I'm going to wait till you're ready. This deals with momentum, so you don't understand this quite yet. Okay? The last chapter showed that changes in an object's motion are related both to force and to how long the force acts and how long that time. The quantity force multiplied by time was called impulse. We're going to come to that in our last unit. How long need not always mean time. It can also mean distance as well. And when we consider the quantity force multiplied by distance, we are talking about a wholly different quantity, a quantity called work. So work is straightforward. It's a definition. It's not derived. It doesn't come from anywhere. It's defined as. It's made up, really. It's defined as force multiplied by distance. We do work when we lift the load against Earth's gravity. The heavier the load, or the higher we lift the load, the more work is done. Two things enter in every case where work is done. There must be exertion of a force, there has to be a force, and there has to be movement. Am I doing work?
There's no movement. It's like anyone can stay perfectly still, so there's like this.
I'm going to try and hold it still, lawyer boy. I'm not working? If I stand here long enough, am I burning calories?
Yeah, you're always working.
What am I doing work?
Yeah.
Okay, what if I do this?
You're working on
Now I'm working? Now I'm doing work, right? I'm converting what to what? Chemical energy in my body, potential energy in my body into kinetic energy, really, right? Oh, kinetic, then potential, right? Kinetic, potential, kinetic, potential, back and forth, right? You're right, no work done. How come? Doctor says no movement. There must be movement for there to be work, which is a simple but yet hard concept. Let's look at the simplest case in which the force is constant and the motion takes place in a straight line in the direction of the force. So we'll start very simple. The work done on an object by an applied force is defined as the product of the force and the distance through which the work is moved. In shorter form, there it is right there. That's all you need to know. Work equals F times D. Work equals F times D. We just took care of this. Defined work is the product of displacement and the component of force parallel to the displacement when the force is constant. We just took care of that. Okay, because the force is parallel in this case. Here's a little guy over here. Work is done in lifting the barbell. If the barbell could be lifted twice as high, the weightlifter would have to expend twice as much as energy. The greater the distance, the greater the D, the greater the work. If you lift 2 loads 1 story up, you do twice as much work as you do in lifting 1 load, because the force needed to lift twice the weight is twice as great. Similarly, if you lift the load 2 stories instead of 1 story, you do twice as much work because the distance is twice as much. Do you do work when you climb the stairs to class? Yes. Are you moving? Yes. Are you applying a force? You're pushing down on the stairs and the stairs are pushing up on you. So that's how you're going to measure. We can easily measure the distance, the height of the stairs. Can we measure how much force you need to apply? Can we? Approximately what force would you need to climb the stairs?
0.
0 force?
Pretty close.
Like, if your weight force is down, say, I don't know, 600 newtons, how much force do you need to get going up?
600.
At least 600, right? 601 to accelerate up. Basically the weight force, right? So what you're going to do is you're going to step on the scale, you're going to measure your weight force in newtons, we're going to find the height of the stairs, and you're going to find how much work you do. And then we're going to convert that to horsepower, which we'll talk about in a while. Note that the definition of work involves both a force and a distance. A weightlifter who holds a barbell that weighs 1,000 newtons overhead does no work on the barbell. Just stand there holding it. No motion. He may get really tired doing so, but if the barbell is not moved by the force he exerts, he does no work. Work can be done on the muscles by stretching and contracting, which is force times distance on a biological scale, but this work is not done on the barbell. Lifting the barbell, however, is a different story. When the weightlifter raises the barbell from the floor, doing work. Work generally falls into 2 categories. One of these is work done to change the speed of something. I went from 0 to some speed when I lifted the tennis balls up, or bringing an automobile up to speed, or slowing it down. The other category of work is the work done against another force, like climbing the stairs. When an archer stretches her bowstring, she's doing work against the elastic forces of the bow. When the ram of a pile driver is raised, it is exerted against the force of gravity. You lift a sledgehammer up high, you're doing it against the force of gravity. When you do push-ups, you do work against your own weight. You do work on something when you force it to move against the influence of an opposing force. Please write in there, often gravity, because it usually is. The unit of measurement for work combines the unit of force, the newton, with the unit of distance, the meter, which means the unit of work is the Newton meter. It's also called the joule. 1 joule, rhymes with pool, is done when a force of 1 newton is exerted over a distance of 1 meter, like if you lifted an apple over your head. For larger values, you speak of kilojoules, thousands of joules, or even megajoules. A weightlifter does work on the order of kilojoules. The energy released by 1 kilogram of fuel is in the order of megajoules. Okay? When you have a Snapple, can I borrow your Snapple, Zach? Is that empty? Okay, I'll get the one out of the recycling bin. I know there's one. I am not going to juggle. I'm not a very good juggler. Snapple has 160 calories. What does that mean? What's a calorie? The unit of energy, right? And when Zach drinks his 160 calories, then that goes into his body and it's stored as fuel, and it uses him throughout his day, right? And if Zach doesn't expend all the calories that he ingests, then those calories are stored as fat. Right? That's biology. Calories is spelled with a large C. You know why? Because it's actually a kilocalorie. No one would drink anything or eat anything if I said, did you know there's 160,000 calories in there? chocolate cake, 200 million calories. People wouldn't eat anything. I don't know, well, they probably would, but these are actually kilocalories. How many calories in here? 170. How many calories in here? 90. Those could all be converted to joules. There is only one food product that I've ever seen that has the energy content rated in joules. Want to guess?
Gatorade, Cervix,
Oh, you know what? Gatorade might.
Cervix energy bars, whatever.
Yeah? Have you got one with you? No?
Oh, yeah.
What kind of energy bars do you eat? Eh? Those Cliff bars? They might. I have never seen one of those. I know that Vector cereal, you know, if you look carefully, it says, yeah. That's what you said. You should have said it louder. You would have been like person of the day. On the nutritional content, on that Vector cereal, it'll list calories and it'll list joules. Why? I have no idea. It's actually, it's actually kilojoules, but again, they don't want to put the word kilo there, or they want to put the actual number. Okay? So, joules. You may have learned about joules in grade 9 science. I teach it, you probably forgot about it, right? When you talk about electricity, do you guys talk about electricity in grade 9 science? Anybody remember?
Yep.
Okay, so there's energy in electricity, and it's also measured in joules. Calories is sort of one of the, it's only for food. But it's defined as a Newton meter. How much it is in electricity is another definition. Okay? What about power? What does power mean? If someone's powerful, what does that mean? Just strong?
They have a lot of force behind them.
Just a lot of force? It's got time, right? It's got time in there, exactly. The definition of work says nothing about how long it takes to do the work. We're on page 2 now. When carrying a load up some stairs, you do the same amount of work whether you walk or run up the stairs. So if I give Steve and Jason identical boxes to carry, maybe there's like yearbooks they're bringing in, there's 50 in each box. Jason decides to run up the stairs. Steve, being the wiser one, takes his time. Sorry, Jason. Takes the elevator. Do they do the same amount of work?
No.
They do. If you subtract their difference in weights, right? They do the same amount of work because the force, the weight of the books is the same. They're tearing up the same distance. They do the same amount of work. But do they have the same amount of power? No. Jason, who decides to run, actually is more powerful. Of course, right? Power is the rate at which work is done. Let me read this here. When carrying a load up some stairs, you do the same amount of work whether you walk or run. So why are you more tired after running upstairs in a few seconds than after walking? To understand the difference, we need to talk about how fast the work is done, which is power. Power is the rate at which work is done. It equals the amount of work done by the amount of time during which the work is done. And we're going to get to this formula. I'm sort of doing an intro thing here. Power equals work divided by time. Power has its own unit, which we'll get to right away. An engine of great power can do work rapidly. An automobile engine with twice the power of another does not necessarily produce twice as much work or go twice as fast as the less powerful engine. Twice the power means it will do the same amount of work in half the time. Generally, power in engines is measured in horses or horsepower. Where did they come up with such a weird unit? Horsepower?
The horses were the ones with the power.
Yeah, they actually determined the power of a standard horse. It was based on how much water a horse could pull out of a well in a certain amount of time, and that was defined as 1 horsepower. Okay? The main advantage of a powerful automobile engine is its acceleration. It can get the automobile up to a given speed in less time than a less powerful engine. So if you've got a big 5-liter Mustang, very powerful, it means it can...
A lot of horses.
A lot of horses, a lot of horsepower. You can get up to speed really quick, right? If you're driving you know what? Last semester it was Dallas's car too that someone said.
A Pontiac 6000 limited edition.
If you're driving a Pontiac 6000 limited edition, so rare because there's very few left on the road, maybe not as powerful. Will it get up to 100 kilometers an hour? Absolutely. Just take a lot longer, right? Is that what Dallas drives? It was. I'm sure it was Dallas's car. He was sitting right there. We can look at power this way. A liter of gasoline can do a specified amount of work, but the power produced when we burn it can be any amount, depending on how fast it burns. The liter can produce 50 units of power for a half hour in a car, or 90,000 units of power for 1 second in a supersonic jet aircraft. How fast you burn it. The unit of power is the joule per second, also known as the watt. And if you were paying close attention in grade 9 science, when we talked about electricity, you would have learned about the watt as well. Like a 90 watt or 100 watt light bulb. Or what? No. Honor of James Watt, the 18th century developer of the steam engine. 1 watt is the power is expended when 1 joule of work is done in a second. A kilowatt is 1,000 watts. Megawatt is 1,000,000 watts. In the United States, we customarily rate engines in units of horsepower and electricity in kilowatts, but either may be used. In the metric system of units, automobiles are rated in kilowatts. I believe in Canada, if you open your car door, there's that sort of plate there, that sticker. It should say horsepower, and in Canada, I think it says it in kilowatts as well. Converts it. Okay? 1 horsepower is about the same as 0.57 kilowatts, or about 750 watts. An engine at 134 horses is about a 100 kilowatt engine. If you've got a 8 horsepower snowblower, what does that mean compared to a 4-horse snowblower?
It shoots the snow twice as far.
Or,
Take twice as much snow in.
yeah, does the same amount of snow in half the time. Right? If you've got a little 4-horse or even a 2-horse, you got to take like a real thin, right? It takes you a lot longer to get rid of it. The 3 main engines of a space shuttle can develop 33,000 megawatts, 33,000, so that's 33,000 watts of power when burned at the enormous rate of 3,400 kilograms per second. That's like averaging the emptying an average-sized swimming pool in about 20 seconds. So imagine the pool over at the rec complex, pull the plug. Ryan, how long does it take them to drain the pool over there? Come on, you must have stood around and watched.
3 hours. Would you call that an average size swimming pool?
I don't know.
I'd say a solid to drain it.
To drain
At
it,
least 2 hours.
I think probably closer to 8.
Uh,
Is that too much? How about,
That's a bit much.
is that right? Would you find out for me?
I could.
Okay, you find out for me. But if you imagine an average-sized swimming pool in 20 seconds, that's how much fuel the space shuttle
Yeah,
burns.
but I don't think that's what they mean by an average size.
No, I think they're talking like an Olympic-sized pool, right? Yeah. So our pool is probably half that size, maybe. Would you say, Ryan, half of an Olympic-sized pool? I don't know, maybe even a quarter.
Would it be the part, like the racing part?
Yeah,
I guess it
yeah. I would say ours is probably considerably smaller than an average-sized swimming pool.
oh, yeah.
Like, yeah. Okay. Mechanical energy. When work is done by an archer in drawing a bow, the bent bow has the ability of being able to do work on the arrow. When work is done to raise the heavy ram of a pile driver, the ram acquires the property of being able to do work on an object beneath it when it falls. When work is done to widen a spring mechanism, the spring acquires the ability to do work on various gears, run a clock, ring a bell, sound an alarm. In each case, something has been acquired. What is this something? This something may be a compression of atoms in the material object, could be a physical separation of attracting bodies, it may be a rearrangement of electric charges in the molecules of a substance. This something, air quotations, that enables an object to do work is called energy. There's your definition. What a lousy scientific definition. Something that enables an object to do work.
Wow.
Now, there's likely a more formal definition, but that's sort of the everyday man on the street kind of definition. Or woman, I shouldn't say man. Human on the street. Like work, energy is measured in joules. Why is it measured in joules? When you have energy, when Zach drinks his Snapple and has 160 calories, kilocalories, that energy can be converted to work when he goes out for a run later tonight. Oh, I was trying to get the spit take there.
That's good.
Yeah. Almost sprayed it all over the brain, right? That would have been funny. Energy is converted to work. And if Zach did go for a run tonight, the 160 calories, he's still laughing about that, would be converted to kinetic energy, right? And then maybe heat. For now, we'll focus on mechanical energy. Energy due to position and the movement of something. Mechanical energy can either be in the form of either potential or kinetic. Let's talk about potential energy. Are we having fun yet?
Yeah.
Well, a little bit. An object may store energy by virtue of its position. The energy that is stored and held in readiness is called potential energy, PE, sometimes known as U. U. I don't know why they use U. Big U, potential energy. Because in the stored state, it has the potential for doing work. A stretched or compressed spring, for example, has the potential for doing work. When a bow is drawn, energy is stored in the bow. A stretched rubber band has potential energy because of the position. For a part of a slingshot, it's capable of doing work. What about in a little 9-volt battery such as this? Is there potential energy in there? Yeah, I'm holding it above the table. Not that kind of energy. What kind of energy is stored in there? Chemical energy, right? It's a battery. It's stored by, you might know something about this chemistry. They pull away the electrons. Protons don't go anywhere, they say, but they pull the electrons away from the protons, create a charge separation. You got yourself a battery, right? Chemical energy. Voltage. That's what this paragraph is about. Chemical energy in fuels is potential energy, for it's actually energy of position when looked at from a microscopic point of view. This energy is available when the positions of electric charges within and between molecules are altered. That is when a chemical change takes place. Any substance that can do work through chemical action possesses potential energy. It's found in fossil fuels like oil, electric batteries, and even in the food and the Snapples that Zach drinks. Work is required to elevate objects against Earth's gravity. The potential energy due to elevated positions is called gravitational potential energy. Water in an elevated reservoir and the ram of power ever have gravitational potential energy. How do we create electrical energy in Manitoba? Hydro dams, which is really just water stored behind a dam. It's gravitational potential energy, which is then converted to electrical as it turns the turbines. Okay?
Did you submit the scores from basketball?
Okay. So, refocus here, you guys. I'm almost done, I promise. Amount of gravitational potential energy possessed by an elevated object is equal to the work done against gravity in lifting it. The work done equals the force required to move it upwards times the vertical distance, W equals Fd. The upward force required is equal to the weight, mg, so the work done lifting it to a height is given by the product mgh. And there, my friends, is the formula for potential gravitational energy. We just covered this one right here. Derive the equation for gravitational potential energy. EP, potential energy, mgh.
What is that?
mgh, mass times gravity times height. It's sometimes written, I've tried to avoid it like this because it usually draws snickers from the crowd.
You know what's in your draft?
Yes. Okay. Note that the height h is the distance above some reference level, such as the ground or the floor of a building. The potential mgh is actually relative to that level and depends only on mg and the height. You can see in the picture below, the potential energy of the boulder at the top of the ledge does not depend on the path taken to get there. So, here we have I have a 100 Newton boulder. It's on top of a 2 meter high ledge. Here it's on top of a 2 meter high ledge. Here it is the same one, right? Except this one went straight up. This one was rolled up a ramp. And this one went upstairs. The potential energy of the 1,000 Newton boulder with respect to the ground below is the same in each case because work is done in elevating to 2 meters is the same whether it's lifted with 100 newtons of force, pushed up the 4 meter incline with 50 newtons of force. Is it easier to go up a ramp? Like instead of going up like this, straight up, is it easier to roll something up a ramp? Yeah, because of you don't have to go straight up. You can sort of like do it over a longer period of time. In fact, your D here is 4 meters, and here the D is only 2. But this one takes less force, twice as long. The amount of work is going to be the same. How come? Because it has the same amount of potential energy no matter how you got there. There's two questions right there. I'm going to go do my attendance, then we're going to talk about them, and then I'm going to stop talking for the day. So read those questions and think about it while I do attendance. How much work is done on a 100 Newton boulder that you carry horizontally across a 10-meter room? Let's say the sleeve of tennis balls is 100 newtons.
That accounts for mg, right? Oh, jeez, I was looking at the answers. That's what I was thinking.
That's why it was hard, because there was no question.
Yeah.
I just carried it across the room. Did I do any work? There was movement. Did I do any work? Compare from there to here. Tatiana, are you calculating or what are you doing? Calculating. What are you punching in? Heather's not typing numbers because numbers don't take that long to type.
No, she is.
Oh, what are you typing? Oh.
Numbers.
She's having trouble.
Because how much work is done? Big fat zero. How come? Hope? Because you look at it. Why is it zero?
Wow.
How much gravitational potential energy does it have right here? X, right? 100 newtons times whatever the distance is, 1.5 meters. How much over there? Exactly the same thing. Did I transfer any energy? I did no work. But now, the lawyer might say you did a little bit of work because you went from 0 meters per second and I accelerated it, I gave it kinetic energy, and then I slowed it down. Did I do that little bit of amount of work? Yes, I did. But I didn't really do a substantial amount of work because I didn't give it any more potential energy. If I do this, then I gave it more, right? So it's got more potential energy, therefore I do work. How much work is done on a 100 Newton boulder when you lift it 1 meter? MGH, the M and the G is already in the 100.
Which formula do you use this? Is it FD one?
How much work is done in a 100 Newton boulder when you lift it? So I'm going to find the potential energy, 100 times 1. Pretty easy to do. 100 joules of potential energy. Therefore, the work is 100 joules.
So are they interchangeable?
Yeah, they're pretty much. Work is done to create energy. Either store it or create kinetic energy or something like that, right? When I rub my hands together and create heat, am I doing work? There's movement.
So yeah.
There's force of friction, my two hands together. I have to be doing work because I'm creating energy. I'm doing work.
Question.
Yeah.
So is joules the unit we use for work?
And
And
energy. Joules is what you use for energy and work. They are, as Steve pointed out, interchangeable. When you do work, you create energy or convert energy. Power is watts. Power is watts. What power is expended when you lift it this distance in 1 second? So if you do 100 joules of work in 1 second, your power is 100 watts. What is brighter, a 100 watt light bulb or a 20 watt light bulb? 100. How come? You get more energy per unit of time. Is a 100 watt light bulb brighter and hotter? Yep. So what about those fluorescent ones that are only 13 watts? How does that work? They're steady. Well, the 100 watt light bulb, you get a lot of light, but you also get a lot of heat. The 13 watt light bulb, you get just as much light, but zero heat. So they're more efficient at converting the energy to just light. So you're losing like about 87 watts of power to heat in a 100 watt light bulb, which is why they're inefficient. Could you heat your home with light bulbs?
yeah, enough light bulb.
Yeah, I guess. It'd be inefficient though, right? It's probably not the most efficient way. Okay, you are likely done listening to me, right? Yes, you can agree with that.